नमस्कार दोस्तों, मैं शिवानंद उपाध्याय आपका स्वागत करता हूं हमारे YouTube चैनल केमिस्ट्री एकेडमी फॉर IIT JEE and NEET. This is the 24th day of JEE Mains revision, and today we are going to cover coordination compounds part 5 in revision series for JEE Main. So today we are going to discuss about isomerism in coordination compounds, and this isomerism in coordination compounds can be divided into two parts: structural isomerism and stereoisomerism. Stereoisomerism further divided into geometrical and optical isomerism. So today we are going to discuss a very small part of isomerism, that is structural isomerism. So in structural isomerism there are 6 types of isomerism. We are going to discuss today these 6 types of isomerism. The first is ionization isomerism. The second is hydrate or solvate isomerism, linkage isomerism. Fourth is coordination isomerism. Fifth is coordination position isomerism. And the sixth is ligand isomerism. Apart from that, we are going to also discuss about polymerization. So when we are discussing about ionization isomers, these isomers have same molecular mass and are produced when the ligand in the coordination sphere and the anion outside the coordination sphere are interchanged with each other. For example, this is an example of ionization isomers in which this ligand Br minus is exchanged from the anion present outside the coordination sphere, that is sulfate ion. So Br minus is going outside and sulfate ion is coming inside. So these ligands which is exchanged should be an anion. These isomers can be distinguished by precipitation method, conductivity method, and ion exchange method. These isomers may have different color because on exchange of the ligands, since ligands have different strength, the crystal field splitting energy is going to change, and because of that they may have different colors. So let us discuss this example. We have written here, that is octahedral complex in which 5 ammonia ligands are there and 1 Br ligand is there inside, and outside in the ionization sphere there is sulfate ion. So here we can only exchange the anion, and there is only one possibility because there is only one anion inside the sphere which can be exchanged with sulfate ion. But here the sulfate ion should act like a monodentate ligand. It should not act like a bidentate ligand. So we know that bidentate ligand or tridentate ligands are also flexidentate ligands. So here sulfate ion is acting like a monodentate ligand. So we can distinguish these isomers with the help of precipitation method. So this complex is reacted with BaCl2 and there is formation of barium sulfate solid. So by weighing the mass and all, we can find out that from 1 mole how much mass we are obtained, and we'll get that how many sulfate ions are there in the ionization sphere. While this complex isomer is not going to react with BaCl2, it is not going to give precipitation reaction with BaCl2, but it will give precipitation reaction with AgNO3. We know that pale yellow color AgBr will form. By weighing, we can find out that how many Br minus ions are outside the ionization sphere. So these two can be distinguished by weighing the mass of the precipitate form. We can find out that how many sulfate ions are outside the ionization sphere and how many Br minus ions are outside the ionization sphere. They can also be distinguished by measuring conductivity of their solution, because this is 2,2 type of electrolyte and this is 1,1 type of electrolyte. 2,2 type means the charge on cation is +2 and anion is -2, and we have studied in electrochemistry that 2,2 type have more molar conductivity than 1,1 type. So by measuring electrical conductivity also, molar conductivity also, we can find out that which type of cation and anion is there in these isomers. Now they can also be distinguished by cation exchange resin method or anion exchange resin method. Like here, if I treat this complex with cation exchange resin method, then in place of 1 cation there is production of 2H plus in aqueous medium, and we can measure the pH and predict about that how much charge is there on the cation. The same way here, when we treat this solution with cation exchange resin, there is production of 1H plus with respect to 1 cation of this complex. So we can also distinguish them by measuring the pH of the solution with the help of cation exchange resin or anion exchange resin. So the other example is PTNH3 4 times Cl2Br2. So here two ligands can be exchanged. So it may possible that both ligands are exchanged, or it may possible that only one ligand is exchanged. So there is possibility of these number of isomers if the formula is this. Then there is a third example where the ligands which are negatively charged, which can be exchanged with the anion present outside. So there are again three possibility over here. We can exchange NO2 ligands with Cl, or we can exchange SCN minus ligand with Cl, right? So based on that, there are three isomers of a compound having this formula. So this is about ionization isomerism. Now let us discuss the second type of isomerism, and these questions are very common in JEE mains. So many questions has been asked in this exam regarding this type of isomerism. Hydrate isomers. This type of isomerism is similar to that of ionizational isomerism. Hydrate isomers are obtained when the water molecule acting as a ligand is replaced by the anion present outside the ionization sphere. So here when we are discussing water molecule is acting like a ligand, and water molecule is neutral and it is going to exchange with an anion outside the ionization sphere. So like if this is the compound where chromium is present in +3, coordination number is 6. So if I am exchanging one water molecule, if I am putting this water molecule ionization sphere and taking this chloride ion inside coordination sphere, then I can write that CrH2O 5 times ClCl2 dot H2O. Again, we can write the other isomer by transferring of two water molecule outside and keeping two chloride ion inside the coordination sphere. So this will form. This is not possible. Why it is not possible? Because water is polar in nature. So in all these compounds, water is present between cation and anion, right? Here this complex will be neutral. So there is no attachment of water molecule with the neutral complex. That's why this is not possible. So that is a common error done by the student. Be careful about this. If the formula is this, there are only three hydrate isomers possible for this compound, right? This is not possible. The third type of isomer is known as linkage isomers or linkage isomerism. This isomerism arises due to ambidentate ligand in coordination sphere. So what do you know about ambidentate ligand? Because in ambidentate ligand, there are two donor atoms, but at a time only one donor atom is attached with the central atom. Like here, Cn minus, here carbon is going to attach with central atom. So it is known as cyano. When we are writing in this form, means nitrogen is going to attach with the central atom. It is known as isocyano. Nitrogen is going to attach with central atom. This is nitro. And when oxygen is going to attach, this is known as nitrito. Same way, sulfur is going to attach, then it is known as thiocyanate. When nitrogen is going to attach, then it is known as isothiocyanate. These two examples are not that important, right? But these four, 1, 2, 3, and 4. OCN minus is cyanato and NCO minus is isocyanate. So sometimes when it is written, when I am writing NCO, it means that nitrogen atom is going to connect with the central atom. When I am writing OCN, then it means that oxygen is going to connect with the central atom. So these isomers can be distinguished by precipitation method, conductivity method, and ion exchange method. They may have different colors because, of course, these ligands have different strength. So delta value will change. Delta crystal field splitting energy value will change, and because of that, the color of the complex may change. So the isomerism due to ambidentate ligand is known as linkage isomerism. Like for example, write down the total number of linkage isomers of the following complex. So first we'll check that in this complex, what is the number of ambidentate ligands. So both are ambidentate ligands. So there are 4 ambidentate ligands. So we can say that when there is no change in any of them, then one isomer will be there, which is this compound. Then what will happen? Case 2, one change is there. I can change either Cn minus, I can write NC, or I can write that this one NCS to SCN, right? So either I will change here or I will change here. Because of that, there are two isomers possible, right? So apart from this compound, I can write by exchange of one. One change means I can write Cu, Cn, Nc, and this will remain same. Or I can write Cu, Cn twice, and this will be NCS and SCN. So because of that, two possibilities are there, two isomers are there. If I do a change of two, what will happen? These two will be changed, or these two will be changed, and the third case is one of this and one of this will be changed. So there is possibility of three isomers from here. Then the fourth case is three change. In three change, either will take this one and one this, or I will convert these two and one this. So there are two possibilities. Or there may be a possibility where all the ligands are exchanged, right? In place of CN, NC twice and this SCN twice. So there is only one possibility. So if I add these all, 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 3 will be 9. So total number of isomers, linkage isomers that is possible is 9. Same way we can find in this complex, all these three are ambidentate ligand. So the first is there is no change, so only one this compound will be there. Now if I go through one change either I will change CN, or I will change SCN, or I will change NO2. So that's why three possibilities there. Two change mein the first case is I will change both CN, or one CN and one SCN, or one CN and one NO2, or I will change SCN and NO2, right? So if you count the number will be 4, right? What I have discussed first was one, दोनों CN को बदल दें, या एक CN और एक SCN को बदल दें, एक CN या एक NO2 को बदल दें, या SCN और NO2 को बदल दें. There are four possibilities, so four isomers are there. In case for three changes, तो उन changes में दोनों CN हो और एक SCN हो, या दोनों CN हो और एक NO2 हो, या तीसरी possibility है SCN, NO2 and एक CN. So there are three changes, three isomers possible here, and the last case is four changes. So only one possibility, all the four will change, right? So if I add this is 1 plus 3 is 4, 4 plus 4 is 8, 8 plus 4 is 12, 12 isomers possible. So linkage isomer is related to ambidentate ligands. The fourth type of isomerism is coordination isomerism, and the isomers are known as coordination isomers. So this type of isomerism is shown by those compounds which are composed of complex cation and complex anion. So this is the first condition, that cation and anion both should be complex. They are obtained when few or all the ligands of both the coordination sphere are interchanged with each other. So there may be a possibility that only one ligand is interchanged between the complex cation and complex anion, or more than one, or all possible. We can change all the ligands between those two, complex cation and anion. The central atom of complex cation and complex anion may be same or it may be different. The coordination number of central atom of complex cation and complex anion may be same or different. During the formation of coordination isomer, the thing which is not going to change is the oxidation state of the central atom into coordination sphere and the coordination number of central atom. These two things should not be changed. So based on that, I have taken one example, write the coordination isomerism of isomers of this compound. So in this compound, chromium is there in +3, and this also chromium is there in +3. By hit and trial method, coordination number is 6. I can write this is +3 -3. And the coordination number is 6 in both complexes. So these two things, oxidation number of chromium and coordination number of chromium, should not change. So let us do scientifically. I have taken this compound. So this is one of the isomer. Now I am trying to exchange one ligand. So when I will send ammonia from here to there and bring one Cl minus here, the oxidation number of the complex cation is going to change, because this is Cl and this should not change. So now it is +2. And here also on the anion, the charge is going to change, because now you can see that this chlorine -5 will go outside, then it chromium will be +5. This is possible, right? This seems to be possible. So this is one of the isomer. Now I'm trying to exchange two ligands. So when I will exchange two ligands, this will form. So on exchanging two ligands, when two chloride ions are inside, then the charge on this cation is +1 and the charge on this anion is -1. So this is also satisfying the condition. So this is the isomer of these compounds. Now, fourth case, if I am going to exchange three ligands, so this and this, then what will happen that chromium, and this is 3 negatively charged, chromium will be there in +3 oxidation state, but now this is not an ionic complex, it is a neutral complex, right? So we'll discard, this is not possible because the first condition is this is obtained where the complex cation, complex anion type of complex compound should be there. So it is neutral complex, that is not possible. Then we are going to do all, like we have till here we have exchanged 3 ammonia, now this is the 4th ammonia. So when this is going to happen, when the chlorine atoms inside the coordination sphere is 4, definitely here the charge will be -1 and here the charge will become +1. So this is repetition of the third case. Third and fifth is the same one. Then we'll exchange 5 number of ligands here. Till here it was 3, then it is 4, now it is 5. So when 5 ligands are exchanged, this is also possible, but we are repeating the same thing. This and this compound, second and fifth compound is same, right? So in this way we have done all the cases. The last one, the sixth one, we can write same way. I can say that the sixth one is, here it is written. So now again this sixth one and the first one is same, right? So the possible isomers, what we'll do, we'll try to draw all the possible changes, and then we'll discard that which is not possible or which is the repeated case, and then we'll find out the total number of isomers. So total number of coordination isomers of this complex is 3. The fifth type of isomer, coordination position isomerism or coordination position isomers. This type of isomerism is shown by those complex compound in which the bridge ligands are present, and these isomers arises due to the exchange of non-bridging ligands between the central atom. Like for this, you can say that these two central atoms are same. It may be different also. So what we are trying to do, these are known as bridge ligands and these are non-bridging ligands. So we are trying to exchange this non-bridging ligands and try to write the IUPAC name. If their IUPAC name is different, it means that it is structural isomers. So here if I am writing NH3 thrice Cl by exchange of one ligand between these two central atoms, so definitely this is different from this value, so it will be an isomer. Then we have done exchange of two ligands, that is also possible, right? When we do exchange of three ligands, right? So when we do exchange of three ligands here, I can write this is equal to NH3 and this will be Cl. So I can write the fourth possibility. I can write here CONH3 and this will be Cl3, and here O2NH2CO. Now this will become 1Cl and 3NH3. So this and this will be the same. If the central atoms are different, then we are able to make another coordination position isomers, but these are same only. So because of that, there are only 3 isomers possible, right? So same way, what we do that, we'll try to exchange all the ligands and try to find out that these compounds are different or same. And from here I find out when I have changed all, 1/4 and second is common, right? So from there we can say that these are 3 isomers possible, coordination position isomers possible for this complex. Now these isomers cannot be distinguished by precipitation method because you can see here that the ionization sphere is same, only the changes are inside the coordination sphere. Conductivity is not going to change because the charge on the cation or anion of the complex ion is not going to vary, and they are also cannot be distinguished by ion exchange method, because if it is anion and if I am treating with anion exchange method, the charge on each anion is same, so there is no going to make any difference, right? So they may have different color, but with the help of color you can distinguish between them. The last type of structural isomerism is ligand isomerism. There are some ligands which exist as isomers. Complex compound containing such ligands will show ligand isomerism. Like here we have written in short PN and TN. So this PN means 1,2 propane diamine and TN means 1,3 propane diamine. So these are isomers. So because of these isomers, the isomerism is known as ligand isomerism, because in this complex you can see here that there are 2 PN, right? Now in place of this I can write 2 TN, or I can write 1 PN and 1 TN. So all these complexes has coordination number of 6 because these are bidentate ligands. So the isomerism developed because of ligand is known as ligand isomerism. And the last point, which is not an isomerism, is polymerization. They have the same empirical formula, two coordination complex having the same empirical formula, where one is the polymer of the other is known as polymerization. It is not isomerism because molecular formula is different. Like here, the first complex I have written that CONS3 thrice, NO2 thrice. So this is the complex. Now the second complex has 2 cobalt atoms, 6 ammonia molecules, and 6 nitrite ions. So if you take the ratio of coordination central atom ligand type of ligand, this is 1:3:3 only, right? So empirical formula will be same. Same way, these two are isomers, right? Because here if you check, these are isomers. So here what we are doing, that we are exchanging the ligands, right? So coordination isomers, right? These two are coordination isomers in themselves, because here the charge on the cation is +3, here the charge on cation is +2, and anion is -2. And this is also coordination isomerism. But we can say that second, third, and fourth are polymers of the first, right? So this is known as polymerization. So this is also very common. We be careful about that. आपस में second, third और fourth जो है वो coordination isomers हैं, but second, third, and fourth are polymer of the first one, right? So that is the point. So hope this is useful for you. In a short time we have revised structural isomerism, and in next video we are going to cover geometrical isomerism, and then we are going to cover optical isomerism. So please don't forget to like and subscribe our channel. Thank you.